In this video, we're going to begin covering section 6.1 in Stewart. So we're going to talk about the area between two curves. Our objective in this video is to interpret the area between two curves as an integral. And so here's our motivating picture here. I have in front of us a graph, simulated of course, of two rates of reaction for two products in a chemical reaction, starting from zero mass. So there's product A and product B. The rate of reaction is how quickly A and B are being produced by this chemical reaction. So in kinetics, recall that rate of reaction is the rate of change of the mass. So as the rate of reaction increases, we're adding more mass. And after a certain amount of time, okay, the products being produced, their rates are changing. So that's why B and A are functions of T. And the area between their rate curves represents how much mass was produced in that time span by A or by B, depending on which one grew faster. So in our case, what we're looking at, let me use let's see. Should I use purple for this one? Sure, why not? So this area here, well, that's not very pretty. Let's do something else. Fine, we'll use red. So this area here, okay, I'm shading in right now. That area between those two curves is what we're going to call the mass gap. So it's the difference in how much more of A was produced than B over that time period. Okay, so the question is, how do we find mass gap when we're just given A of T and B of T? And that's the objective of formalizing what area between two curves looks like. So let's talk about it. So I'm going to again draw a similar graph here. And in this case, our variable is going to be x, okay? And here we have y. And I'm going to have two curves. And we want to formalize what we mean when we say the area between two curves. So these functions are going to be f of x, f of x and g of x. So two functions of x. And they bound this region in the plane over the interval A to B. That really could be considered 0, but we're just going to, for the sake of clarity, call that A. And now I'm going to draw in a rectangle. No. Oops. No, that's not what I wanted either. Nope. Oh, close enough. So this rectangle, okay, is going to be one of our infinitely thin slices. okay? So let's identify some of the pieces here, okay? So this infinitely thin slice has a width of what we're going to call delta x. And we're going to have the height be the difference between f of x and g of x. But how do we know what x to pick out? So, and this is a review of our standard techniques in chapter 5, where we're going to construct a Riemann sum. Where we assume we're going to partition our interval that we're talking about using sample points. X sub I star. Okay, so somewhere in here, say here, we have our x sub I star. And so that's our candidate for setting up f of x sub I star minus g of x sub I star. Okay? So that means that the area of this infinitesimally thin, so the infinitesimally thin rectangle has area f of x sub I star minus g of x sub I star times delta x. And since we're talking about converting this into an integral, logically, the Riemann sum then, if we're setting up a subdivision using n sample points, means the Riemann sum is going to be the approximated area is the sum from I equals 1 to n of these a sub i's. In other words, we suppose that the area under the curve, the area between the two curves, is approximately the sum of the difference between f and g times that infinitely small width, delta x. And in the limit, so as n goes to infinity, so we subdivide even smaller and smaller and smaller, okay? So to understand that better, I'm going to go ahead and draw that again. Whoops, not that. Here we go. Here's our drawing again. What we're actually talking about here is some really thin slice there, okay? We're going to add all those up together, okay? So that's our infinitesimally thin slice, okay? That we hope is going to add up to be the entire area. And so what that ends up looking like is, because in the limit, the Riemann sum becomes an integral, where you're talking about the integral from a to b of f of x minus g of x dx. So the important pieces here to recognize are, this is the integrand, and here's our dx in the limit. Okay, so the important pieces here to remember are that this is the upper curve, this is the lower curve, A is the left endpoint, and B is the right endpoint. Okay, and it's a positive quantity because we assume some important things such as, so if I put an asterisk here, okay, our asterisk here, all the underlying important math things that we actually need for this to work are that the area is a positive quantity and well defined because we assume f and g are continuous over that interval a, b, and we assume f of x is greater than or equal to g of x for all x in that interval. If that fails, then we'd have to split it up into two integrals, and that's the topic of a different video. But just as an example, okay, we're gonna do a quick do a quick example here. So example. We're going to express the integral for the area between the curves y equals 1 over x plus 2 and y equals x plus 2 squared between x equals -1 and x equals 1. Okay, so one thing to note here is that when you are setting these up, if you do not have a clear picture of what the curves look like, feel free to graph it using, for instance, Desmos. So right now, I do have a clear visual of the picture here, thankfully, because I did this ahead of time. And so I have, here's -1, here's 1, okay. And 1 over x plus 2 looks roughly like this. Okay, that's y equals 1 over x plus 2. Meanwhile, x plus 2 squared looks roughly like this. Actually, I'd like to make that a little sharper, just because there's more curvage going on here. Okay, so we're only talking about between 1 and -1. So that area that we're talking about, an infinitesimally thin piece of it, would be something like this, okay? But the full area between the two curves would just be something like this whole segment here and this whole segment here. It doesn't actually stop. I stopped so that I could still highlight the infinitesimally thin slice there. And then the integral then, making sure that the upper curve, it was first, means that we're integrating from -1 to 1, left endpoint, right endpoint. And our integral is of x plus 2 squared minus 1 over x plus 2 dx, which we're not going to do right now, but this is how you would set up that calculation, and you will find at the end some real number, positive, that represents the area between the two curves.